Welcome to the deep dive. Today we're looking at globular clusters. Think, ancient cities made of stars, all tightly packed together by gravity.
That's a great image. Very different from the looser open clusters we see.
And for ages, getting a handle on these stellar cities, especially how far away they are, it was a real challenge, even with our best telescopes. Until pretty recently, actually.
Absolutely. They're true relics. I mean, these globular clusters are leftovers from the very early universe.
Not like the younger open clusters you find hanging out in the Milky Way's disk where we are.
Exactly. Globulars are some of the oldest things in our galaxy. And they're everywhere, the disk, the central bulge, but especially out in the halo.
That huge sphere surrounding the whole galaxy.
That's the one. A vast area.
And we know of what, over 150 in the Milky Way alone?
Yep, more than 150 found so far. Some are relatively close to the galactic center, maybe a few thousand light years out.
Kiloparsecs, you mean?
Right, kiloparsecs. Others are way out in the galactic boonies, maybe 30, even 40 kiloparsecs away.
Wow. And the nearest one, M4, is still about 2.2 kiloparsecs off.
Still a fair trek, yeah. And it's not just us, other galaxies have them too. Lots of them.
Their age is pretty mind-blowing, though, comparable to the universe itself.
Pretty much. They formed way back when the universe was, just getting started. Some might even be the leftover cores of small galaxies the Milky Way gobbled up.
Galactic cannibalism remnants.
Kind of, yeah. So even though they're just a tiny fraction of the galaxy's light or mass, they're like cosmic fossils, super important for understanding the galaxy's history and how it moves.
Okay, so they're ancient, important, and really far away. Measuring stuff about them, like distance, was super hard then.
Oh, incredibly difficult. Take the Hipparcos satellite back in the 90s, fantastic mission, but even the closer globular clusters were just too far for it to measure their distance directly using parallax.
Parallax, that's the tiny wobble we see in a star's position as Earth orbits the sun, right? It gets smaller the further away it is.
Exactly. And the stars in these clusters are mostly pretty faint and packed incredibly tightly together. Imagine trying to measure one specific light bulb in a packed stadium from miles off.
Yeah, tricky. Very tricky. So no direct readings from Hipparcos for these clusters.
No direct distances. But Hipparcos wasn't useless for them, not at all.
Ah, okay. How did it help then?
Well, Hipparcos nailed the distances to certain types of stars near us in our galactic neighborhood with really high accuracy.
Okay.
And here's the clever part. We find those same types of stars inside globular clusters. So if we know how intrinsically bright that type of star is supposed to be, based on the nearby ones Hipparcos measured,
You can see how faint they look in the cluster and figure out how far away the whole cluster must be, like a standard candle.
precisely. It's all about calibration. Knowing the wattage of the bulb tells you its distance based on its apparent dimness.
And this helped figure out the ages of the clusters, too.
Yes, exactly. Get a good distance, and you can figure out the true brightness, the luminosity of the cluster stars. Then you plot them on a Hertzsprung-Russell diagram.
The brightness versus color plot.
Right, and you look at the main sequence where stars spend most of their lives fusing hydrogen, like our sun. The point where stars start to peel off that main sequence tells you how old the cluster is. Older cluster, the turnoff point is lower down.
Okay, but this led to a bit of a headache, didn't it? Before Hipparcos, there was this age paradox.
A major headache. A real cosmological crisis, actually. Back then, maybe mid-90s, estimates for the Hubble constant, how fast the universe is expanding, suggested the universe might only be, say, 8 to 12 billion years old.
Right, based on how fast things seem to be moving apart.
But then the age estimates for the oldest globular clusters, like one called NGC 6941, were coming in at 15 billion years, maybe even older.
Oh, how can stars inside the universe be older than the universe itself? That doesn't work.
It certainly doesn't. Big problem. But Hipparcos data offered a way out. It measured nearby Cepheid variable stars really well.
Those pulsating stars. Good standard candles, too.
Excellent standard candles. Their pulsation period tells you their true brightness. People like Feast and Catchpole used Hipparcos data in '97 and found Cepheids, like those in the Large Magellanic Cloud, were actually further away and therefore intrinsically brighter than we thought.
Okay, further and brighter, how does that fix the age paradox?
Well, if the nearby Cepheids used for calibration were further and brighter, it implied the more distant Cepheids used to measure the Hubble constant were also further and brighter.
Ah, so the universe wasn't expanding quite as fast as we thought.
Exactly. A smaller Hubble constant means an older universe. At the same time, realizing globular clusters were also likely further away meant their stars were intrinsically brighter too, which slightly lowered their age estimates when recalculated.
So the universe got older, the clusters got a bit younger.
And the paradox eased. Phew.
Makes sense. Did Hipparcos look at other star types and clusters, like subdwarfs or RR Lyrae stars?
It did. Subdwarfs are old, metal-poor stars that pass near us. Hipparcos could measure them, and since they're similar to cluster stars, that helps calibrate distances using that main sequence fitting method we talked about.
Okay.
R Lyrae stars are another type of pulsating variable, very common in clusters. But even the nearest ones were really pushing Hipparcos' limits for good parallax. So useful, but not the super precise measurements needed.
Really showing the need for something more powerful.
Definitely. Something that could reach further, see fainter, measure angles much more precisely.
Which is the perfect lead-in to our main focus for this deep dive, Omega Centauri, also known as Milky or NGC 5139. This one's special, you can actually see it with the naked eye from the southern hemisphere.
That's right, in the constellation Centaurus. Edmund Halley, the comet guy, actually cataloged it as something fuzzy, non-stellar way back in 1677.
And it's not just any globular cluster, is it? It's kind of the king.
It really is. It's about 5,200 parsecs away. That's over 17,000 light years. And it's the biggest and most massive one we know in the Milky Way. Easily.
How massive are we talking?
Estimates are around 10 million stars. Total mass maybe 4 million times the mass of our sun. Just enormous.
10 million stars.
Right.
Wow. And it's physically huge, too. About 50 parsecs across.
Yep. Which is why, even though it's so far away, it appears almost as big as the full moon in the sky. Quite amazing.
And there's that theory it might not even be a true globular cluster.
Well, there's strong evidence suggesting it could be the leftover stripped-down core of a dwarf galaxy that our Milky Way captured and tore apart long ago.
A galactic fossil, indeed. But like you said, way too far, way too crowded for Hipparcos to get good parallax measurements on individual stars inside it.
Exactly. Too far, too dense, too faint for Hipparcos. We had estimates, good ones, but not that ultra-precise direct measurement.
But that's where the game changes.
That's where Gaia comes in.
Right. The European Space Agency's mission, mapping billions of stars with just unbelievable accuracy. So our mission today, using a key paper by Soltis and colleagues from 2021, is to explore how Gaia, especially its early data release 3, has totally transformed our view of Omega Centauri's distance.
And what that precision means for, well, for understanding the whole universe.
Okay, let's get into it. The Soltis paper. What was the big Gaia breakthrough for Omega Centauri?
It all comes down to Gaia's incredible power to measure parallax, that tiny angular shift. For the very first time, we got direct trigonometric parallax for a huge number of individual stars within Omega Centauri itself.
Not just relying on assumptions about star types anymore.
Precisely. Soltis and the team sifted through Gaia's early data release 3 data, looking at something like 178,000 stars within about 45 arc minutes of the cluster center, a huge patch of sky around it.
Wow, that's a lot of stars. How did they pick out the actual cluster members?
Good question. They use Gaia's proper motion data, that's the star's movement across the sky. Cluster members should all be moving together, right?
Like a swarm of bees.
Exactly. And their measured proper motions agreed well with previous studies, which gave them confidence. Then they used Gaia's photometry, the brightness and color data, to place stars on that color magnitude diagram.
And pick out the ones that fit the known pattern for Omega Centauri's stars.
Correct. After all that filtering, they ended up with a really clean, high-quality sample of over 66,000 confirmed members with excellent position and brightness measurements from Gaia.
66,000 stars. And what did their combined parallax tell us? The definitive distance.
Pretty much definitive, yes. They calculated a mean parallax for the cluster of 0.191 milliarcseconds, plus or minus just 0.001. It's incredibly precise.
Tiny angle. What's that in light years or parsecs?
That translates to a distance of 500 and 236 parsecs with an uncertainty of only about 28 parsecs, so roughly 17,070 light years.
And how does that compare to the older estimates, like the Harris one you mentioned?
Really good agreement. Harris's classic estimate from '96, based on his photometric methods, was 5.2 kiloparsecs, so 5,200 parsecs. Gaia's direct measurement basically confirms those older methods were remarkably accurate for Omega Cent.
That's reassuring. Okay, so we've nailed the distance. Fantastic. But you said this has bigger implications for cosmology, involving something called the tip of the red giant branch.
Yes, the TRGB. It's a really crucial feature.
Explain that for us. What is the tip of the red giant branch?
Okay, so think about stars like our sun, maybe a bit less massive. When they finish burning hydrogen in their core, they evolve off the main sequence and become red giants.
They swell up, get cooler on the surface, hence redder.
Right, and they get much, much brighter. They climb up what we call the red giant branch on that color magnitude diagram. But there's a peak brightness they reach.
A maximum point.
A maximum point, yes. That's the tip. It happens right when helium fusion suddenly ignites in the core something called a helium flash. After that, this star actually adjusts, gets slightly fainter again for a bit.
So that tip represents a very specific physical event in the star's life.
Exactly. And importantly, the luminosity, the intrinsic brightness of stars right at that tip, is remarkably consistent for these kinds of old, low-mass star populations you find in globular clusters and galactic halos.
Ah, consistency means standard candle potential.
Bingo. If you can reliably identify the brightness of the TRGB in a distant galaxy, and if you know its absolute magnitude, its true brightness.
You can calculate the distance to that galaxy based on how faint the tip appears.
Precisely. And this method is super valuable for measuring distances to galaxies that host type Ia supernovae.
The exploding white dwarfs, another key standard candle.
One of the most important, yeah. They take us way out into the universe and are fundamental for measuring the Hubble constant. So you need accurate distances to the galaxies where they explode to calibrate their brightness. The TRGB is one way to get those distances.
I see the ladder forming. You calibrate the TRGB using things like Omega Centauri, then use the TRGB to calibrate supernovae distances, then use supernovae to measure the universe's expansion.
That's the cosmic distance ladder, yes. Yeah. And getting the first rung right, the calibration of things like the TRGB is absolutely critical.
And Omega Centauri, now with its Gaia distance, is perfect for calibrating that TRGB.
It's pretty much the ideal place in our galaxy. Before Gaia, nailing down the TRGB's absolute brightness was tough, partly because of distance uncertainties to clusters.
Right.
But also, most globular clusters just don't have that many bright red giants right near the tip. It's a relatively short phase. You need a huge number of stars overall.
But Omega Centauri has millions.
Exactly. It's got so many stars, including like almost 200 red giants, very close to the tip brightness. It gives you fantastic statistics to really pinpoint where that tip is.
So the Soltis paper used the new Gaia distance for Omega Centauri to calculate the absolute magnitude of its TRGB.
They did. They found the I-band absolute magnitude, this brightness measured through a specific infrared filter, is negative 3.97, with a really small uncertainty, just minus 0.06 magnitudes.
Okay. And how does that compare to previous calibrations used for Hubble constant work?
It's interesting. It's actually slightly fainter than some widely used calibrations, like one by Wendy Friedman and her team from 2019. About 0.07 magnitudes fainter.
Doesn't sound like much, 0.07 magnitudes. But does that small difference matter for the Hubble constant?
Oh, it absolutely does. Remember the distance ladder? Small changes on the lower rungs get magnified further up.
Right.
According to Soltis and colleagues' calculation, using this slightly fainter TRGB calibration increases the value of the Hubble constant derived from type Ia supernovae by about 3.2%.
Okay, so what's the new number then?
The revised value, based on this Omega Centauri TRGB calibration feeding into the supernova ladder, comes out at 72.1 Grenian 2.0 kilometers per second per megaparsec.
72.1.
Yeah.
Right. Now, where does that number sit in this whole Hubble tension discussion we hear so much about?
Smack bang in the middle of it, really. This value, around 72, agrees quite well with other local measurements of the Hubble, constant measurements made using things like Cepheid variables in nearby galaxies, often giving results around 73 or 74.
Okay, so the local measurements seem to be clustering together.
They do seem to be converging. However, it's significantly higher than the value you predict based on observations of the very early universe, specifically the cosmic microwave background radiation measured by the Planck satellite.
The echo of the Big Bang.
Exactly. Planck data, when fed into our standard model of cosmology called lambda CDM, predicts a Hubble constant closer to 67 or 68.
So there's still this gap, a pretty significant one statistically, 72 versus 67.
A very significant gap, roughly a 4 to 5 sigma tension, depending on exactly which data sets you combine. That's scientists speak for very unlikely to be just a fluke.
So fascinating. Hipparcos helped solve the age paradox by getting better distances, making the universe older and clusters younger. But now Gaia, by giving us even better distances, like for Omega Centauri, is refining tools like the TRGB, and it seems to be confirming, maybe even sharpening, this Hubble tension.
It certainly seems that way. The local universe measurement seems stubbornly high compared to the early universe prediction. The mystery of the expansion rate persists. We understand the distances to these old stars better than ever, but why the expansion rate measurements disagree? That's still a huge open question.
It's amazing that studying this one giant ancient star cluster in such detail feeds directly into these absolutely fundamental questions about the cosmos. And Gaia didn't just give us distance for Omega Centauri, right? The paper mentioned other things.
Oh, absolutely. Gaia's data is so rich. They talked about using it to map Omega Centauri's 3D structure, figure out its depth along our line of sight, trace its orbit around the Milky Way much more precisely, and even study the tidal streams the stars being pulled off it by the galaxy's gravity. It's a revolution for studying the cluster itself, too.
So the age paradox is mostly settled history, thanks partly to Hipparcos, but the Hubble tension is very much alive and kicking, maybe even getting more tense thanks to Gaia's precision on objects like Omega Centauri.
That sums it up pretty well.
It really makes you wonder, doesn't it? What else will we learn as we keep digging into Gaia data, keep probing these ancient structures? Could the key to understanding the universe's expansion be hidden somewhere in the details of objects like Omega Centauri? That's definitely something to think about. Thanks for joining us on this deep dive.